This lesson we're going to look at composite functions. So first of all, what a composite function means is you're putting one function into another. So for example, you may have seen questions like this back in Math 10C where you were given a function, say as x squared plus 2x, I'm just making one up here, and then you may have been asked to find f at f. F at 5 or any number. So then all you would do is you would substitute that 5 into every variable in that function. Now, instead of substituting a number into another function, you can actually substitute another function into a function. So what that means is instead of substituting that 5, maybe you're substituting a different function, such as, let's make g at x 5x. Okay, so now I'm substituting that 5x into all of those variables. So that's what we're going to be looking at today. So instead of just substituting a value, we're going to be substituting another function into a function, or even a function into itself. All right, so let's start by evaluating a composite function. So the other thing I'd like to point out to you is notice how the dot used in compositions is not circled in. So that looks different than the dot used in multiplication. So that's something you want to watch out for. So this means composition of two functions, while this means a multiplication of two functions. So for me, the first step whenever I'm doing this is I actually like to rewrite this, because this actually means the same as this. I'll rewrite it in that function notation form. So here I'm going to rewrite this as f at g1. Okay, so what this means is we're going to start on the inside and work our way out. So we're going to take 1 and input it into the g function, which is 4x. So if I were to substitute 1 into 4x, I'd end up with 4, right? Because 4 times 1 is 4. So now that I know that, I'm going to take that 4 and substitute it into my f function. So 2 times 4 to the third minus 3 gives me 125. And then I'll do the same for the next few. So this time I'll always rewrite it. So I'm taking the 1 and substituting it into the f function. So 2 times 1 to the third minus 3 gives me 2 minus 3 is negative 1. Okay, so now I know I have g at negative 1. So I'm going to take that negative 1 and substitute it into the g function. So 4 times negative 1 is negative 4. So you can see that f at g at 1 and g at f at 1 actually gives us very different answers here, 125 versus negative 4. Okay, so the order does matter in which these functions are written in. And then you can also put a function into itself. So what that looks like, and I'm running out of room, so I'm just going to write this down a little further. So now we're going to go to the f function and substitute negative 2 in. So we have 2 times negative 2 to the cubed, okay, minus 3. So 2 times negative 2 cubed minus 3 ends up giving me negative 19. Now I'm going to take that negative 19 and substitute it into f again. So 2 times negative 19 cubed minus 3, and you can just type this in your calculator. My final answer would be negative 13,721. And I actually don't think you have this one in your notes. We'll just move on here. All right, so the next section in my notes here, if I'm looking, is you're going to see the graph. So just like with multiplication and division and addition and subtraction, we could find the multiplication of two functions using a formula or a graph or a table of values. The same holds true with a composition. So now we're going to show you what that looks like. Okay, so again, I'd always start with the inside. So I'm going to just look at my g graph and find negative 4. So ignore that f graph. Just look at your g graph and figure out what is the y value when x is negative 4. So we're going to look at where x is negative 4. We know the y value is 0. So what we're going to do is we're going to substitute 0 in for that function. So now we're going to go to our f function and figure out the y value when x is 0. And we figure out that it's 2, positive 2. So then my final answer is positive 2. Okay, let's try the next one. So for b, we start at the g function. We're starting on the inside. We're looking for where, and I'm going to use a different color here, where x is 0, right? So that means when x is 0, so I'm going to start at 0. My g function is -4. So all I'm going to do is replace that with the -4, and then I'm going to go to my f graph and figure out the y value when x is -4. So when x is -4, my y value on my f function is positive 2. So then my answer, once again, is positive 2. All right, I'd like you to pause this video and try C and D by yourself, and then I'm going to put the answers on. Okay, so the answers for C and D, and I'm not going to go through a lot of detail just for time's sake. You should be getting -4 for C and -5 for D if you did it correctly. All right, moving on. So my notes are kind of backwards here. All right, and I don't think I have all these examples, which is good. So we're just going to do this one and this one. So now we can determine the equation of each composite function and then state its domain and range. So let's start here. So what we're doing is we're taking our f function and we're inputting our g function. That's what this means. That's what that notation means. So I like to just write my f function out. I'm going to write y equals x plus 1. And then I'm going to substitute that g function into the f function. So anytime I see a variable, like this x here, I'm just going to substitute that g function in for that variable. So this is my new answer. So y equals x squared plus 1. And it's really important that you're watching that notation. So sometimes I'll have kids who just get rid of the y, or whatever that notation is, and then it's an expression instead of an equation. That's where you lose those little nitpicky marks, so watch for that. Okay, so now if you were to graph this, it's a quadratic, so the domain then obviously would be, without even graphing, we know it's going to be x is an element of all real numbers. So I'm just going to write that in interval notation. Okay, and then if you were to graph it, the range, and I might graph this really quickly, x squared plus 1, I'm assuming it's probably greater than 1, but we'll graph it just to double check. Yep. So then my range would be from -1 to positive infinity. Okay, there we go. And now you can try the same with the f function. So you have y equals, so we're putting the f function into the f function. So again, I like to actually just write out my f function and start there. And then I replace any variable with the f function. So I'm replacing this variable with x plus 1. So I end up with x plus 1 plus 1, which gives me, if I simplify, x plus 2. So I have a linear graph here. So obviously with any linear graph, your domain would be x is an element of all real numbers, and your range would be y is an element of all real numbers. There we go. Okay, moving forward. Hey, look, there's some unicorns, just to make the question that much more fun. Okay, so let f at x equal x plus 1 and g of x equals x squared. Determine the equation of each composite function and state its domain and range. Actually, we already did this one, didn't we? Yeah. Okay, we just did that. I guess I forgot to delete that slide. Okay, determine the original function from a composition. So this time you get to do some backwards thinking. Fun. So they're giving us the answer, which is at h at x. And they're saying h at x is a composition of the g function inputted into the f function. So what could be a possibility for the f function and g function? Okay, in order to end up with this equation. So there's actually, I can think of two different answers here. Again, backwards thinking. So I could see the f function could be x squared plus x plus 1. And the g function, which you're inputting into that f function, would just be the x minus 2. So that's definitely a possibility. Another possibility, which this would work for almost every question, you could say, and you only need to give one answer here, but I just wanted to show you two just so you can kind of think of it different ways. You could say the f function is just x, and then the g function is this entire expression that you're inputting. That's another possible answer. Okay, and you're inputting this entire function into that x. All right, so this is a couple old diploma questions now. So given that f at x equals the square root of x minus 1 and g of x equals x squared plus 3 and h at x equals 2x minus 5, if k at x equals h as a function of g as a function of f, determine a simplified expression. So what I'm going to do is I'm actually, because I prefer the other notation, it just makes more sense in my head, I'm going to rewrite this because I like it written this way. Okay, and now we're trying to determine a simplified expression. So we're looking for an equation here. So we know k at x equals, and I'm going to just start with the g at f at x. So I might actually write this on the side of my paper. Let's use a different color here. So g at f at x. Okay, I'm just starting with this little part here. So I'm taking that g function and inputting the f function. So I'm replacing all the x's, so in this case I just have the 1, with that f function. So I'm replacing the x with root x minus 1 squared plus 3. Okay, so then what ends up happening is that square and the square root cancel out, so then I'm just left with x minus 1 plus 3. And then from here I can collect like terms, and I end up with x plus 2. Excellent. So now I'm going to replace that whole thing with x plus 2, that answer that I got there. Let's use a different color even. Okay, so now I'm taking that h function, where's the h function? Here it is, and I'm replacing that x with x plus 2. Okay, and then from there I can simplify. So I have 2x plus 4 minus 5. I'll collect like terms from there. And I have 2x minus 1 as my final answer. Okay, so this is the simplified expression. However, the domain is tricky. Watch for this. I always have kids make this mistake. So whenever we're simplifying expressions, and this deals with rationals as well, you have to look at each individual step and consider the restrictions of that step. So because we have a radical here with an even index, a square root, in other words, we can't have a negative square root. So even though that square root symbol cancels out with the squared, that rule still applies, that restriction still applies. So that means because we can't have a negative square root, our x value would have to be greater than or equal to 1. All right? So something I suggest to kids is I might even graph this before I input it and see if there's any restrictions too if I want to double check. So in my domain would be that for all x values, and I'm writing in set notation this time, x would need to be greater than or equal to 1 where x is any real number. So watch for that when you have restrictions. Even though you might have a simplified expression that doesn't have a restriction, you have to consider every single previous step. Okay, next question. I'd like you to try this one by yourself. So I want you to press pause, okay, try the question, press play, and I'll explain it really quickly. Okay, so this time we are doing finding an h value function and inputting the f function into the g function. So we're taking our g function, which is x squared over x squared minus 9, and we're replacing all of our x's with that f function. And I'm going to use another color here, which is root x minus 3. Oh, okay, I don't know what I pressed there. So once again, the square and the square root cancel out. So then we're just left with x minus 3 over x minus 3 minus 9. And then from there I can collect like terms. So on the denominator there, we can collect the -3 and -9, and we end up with x minus 12. And I'm running out of room, so I'm going to write this on top here. Okay, but similar to the question we did before, there's still restrictions. You have to consider the restrictions of every single step. So here we do have a restriction, right? Because we can't have a negative radical. So that means x would have to be greater than or equal to 3. We also have a restriction in the fact, for our domain here, that we can't have a denominator in our simplified expression, right? That would equal 0. So that means x could not equal 12. So that would be my domain. So x would be greater than or equal to 3, but x could not equal 12, so my answer would be 4. Oh, there we go. Okay, last question. Okay, so this time they give us a value. Whenever we're given an x value and we're asked for a value, we're looking for an answer. There's lots of ways you can do this. So we're inputting 5 in for h. So really, this is what we're doing. We're inputting, wherever I see an x, I'm inputting a 5 there. And again, I like this other notation. So I'd probably start this in steps. So I'd start with the g at 5s, and I'd go to g and replace the x with 5. So 1 over 5 minus 2 is 1 over 3. And now I'm going to replace all of those g at 5s with 1 over 3. Okay, and now from here, I'm going to take that 1 over 3 and replace the x with the 1 over 3. Okay, and you could even type this in your calculator if you wanted at this point. That's absolutely fine. But I'd end up with 1 over 9 plus 6 times 1 over 3 is just 2. Okay, so then if I round to the nearest hundredth at this point, I would just type this all into my calculator, and you could do it earlier than this, and you'd end up with 2.44 rounded to the nearest hundredth. All right, here's some questions for you to try and a little math joke. This is what putting the pineapple into the pizza would look like, and what putting the pizza into the pineapple would look like.